Welcome back to High Performance Computing, Advanced Scientific Computing. Today, the lecture is about hybrid programming and patterns, and it connects nicely to the previous lectures we had in the beginning of the course, starting with MPI, then get a better understanding of domain decomposition, parallelization, and then in one of the last lectures, really OpenMP as shared memory programming. Today, we will connect some of these lectures and then also introduce certain patterns, which also nicely connects us to the second half of this course, which is more about the applications that really give rise to HPC, why we need high performance computing, why we need to scale up really. But before we go into the material of that lecture, let us review what we had the last time. And we looked at practical lecture 6.1 as a way of really getting hands-on experience of shared memory programming. And the first thing to take away message was really thinking that we have different threads that basically have here and there so-called parallel regions. So there is a so-called master thread that we will pick on today as well in our lecture, but it has a lifeline, and every now and then marking a certain parallel region, we will look at basically getting several threads for helping. And this could be different work sharing constructs. We looked at for loops, for example, which are a very prominent way to do so, but also other, let's say, work sharing constructs. And the naming suggests that these are really lightweight threads. So they are not this heavy processes and so on that we know from the MPI world. And the other idea is, of course, here, instead of communicating wildly between these threads, which happen to be all in one node, all share memory, we basically use, of course, a shared address space. So rewriting to memory and reading from memory, because that is very fast. And of course, we can do so because essentially every one of these threads, which is joined here or basically forked here and then joined here again, these threads here have, of course, all a shared address space. And with this, it's a very efficient way of do communication, really. We just communicate, so to speak, through variables and values. But on the other hand, of course, we also have seen that this raises issues. We had critical regions where there are certain race conditions among some variables. Let's consider that one thread is writing X while the other thread is reading X to do some addition or multiplication, whatever. And another thread is using X for another multiplication or addition as well. So all of those at the same time now basically want to read and write the variable X at the same time. And we have learned that this is, of course, a problem and will not lead to deterministic outcomes. So there were critical regions and more advanced algorithm parts that we can put in shared memory programs really to prevent this from happening. But the general understanding was largely connecting it perhaps a bit from what you have seen already, was basically submitting lots of MPI applications in your first assignment and also in our previous lectures. It is very similar. So I still have a submit script that I do in SBatch with. I do this on the Utune login node or on any other login node. And the Hello Threads job here that you see is basically similar, except maybe a little bit from this particular aspect where we have CPU per task, where we identify how many threads we want to spawn on this process. And essentially then also telling the environment a little bit, the OpenMP environment, how many threads we're going to use. With this, we also see that Hello Threads itself, when we basically come to the source code, that we basically compile as we have learned before with GCC, but we have to also do an additional -f OpenMP just to say that we have compiler directives that actually have the Sentinel or this OpenMP basically indicators of doing some pragma OMP statements in order to do parallelization at certain parts. So with this, we have an application which is scalable to the number of threads I put here. So when I do Hello Threads, I have 4 here as an example, but nothing prevents us to put here an 8 in these basically job script areas, or a 12 or a 16. And we will see that the Hello Threads automatically scales up and will basically then execute these parallel regions with 12 threads. Obviously, that was a very simple program, but it connects nicely to what we learned before, that you see the way how you do shared memory programming at large is very similar to distributed memory programming from the, let's say, 10,000 feet perspective, but then we have to differentiate really, thinking about that each of those that really do some work are not full-blown full-blown processes. They are threads that are very lightweight because they carry away the same pointers to the shared address space. Today, we will learn how to connect this now with basically full-blown MPI processes that all of them actually have the power to kickstart threads. And we come to very complicated programs from a parallelization point of view. But of course, also, if you remember, we have seen in HPDBScan in this clustering algorithm as one example application. This carries, of course, a good chance to scale up to have even a better performance if you combine the power of distributed memory programming basically across the nodes and then shared memory programming within the node. Still, it's not for beginners. It's a topic which is a little bit more advanced. Hence, we are basically through the half of the course already, and we're entering more advanced parts here of the HPC lectures, leaving behind, so to speak, the beginner lectures. And now we will connect in lecture 7, 8, and 9, and then the subsequent ones with real practical application areas, really more advanced parts of HPC. So today is a topic with hybrid programming, which in other words is not something which you should start with as a beginner, but really to optimize, to tune, to fine tune really your application later. So looking on the source code again, we have seen the Sentinel, Pragma OMP parallel. We have learned a little bit about the private elements to have, let's say, a copy of each of these different variables for each of these different threads, which connects to another important part here. You already also a little bit can connect to, because we had always this rank 0 as a special process. The same is actually possible if we get the TID here, the thread ID from the OpenMP environment, where I can differentiate from. So at each of these different threads in this parallel region, get a specific thread ID that we can use to differentiate. And you see here, almost like we did with rank 0 in our earlier lectures with MPI, we can connect here with the thread ID being 0, meaning that just the master thread of sort here, this one with a lifeline of the program, basically will only execute this particular part of the program. While all of this is, of course, executed in parallel, we have the Sentinel here with the Pragma OMP parallel statement. So this will be 4 times, 8 times, or 12 times executed, depending on how many threads you actually have pointed here. But essentially, beginning with this unique thread ID, I can really influence the application logic again to really make that to some specific use. And basically, the Hello Threads compilation using FOpenMP I already said. Just the final aspect of connecting to the last lecture, when we think about more, of course, advanced applications, advanced in a certain sense of saying real work sharing construct, and not this hello world printf statement. There we have seen that one of the most uses of basically OpenMP today is probably the Pragma OMP parallel for a for loop. And so basically here we have an idea of a whole parallel region. And within this parallel region, we have different threads working there. And we see here that we have a for loop, which is this Pragma OMP for statement that I can schedule in dynamic chunks, the chunk size I define, as we learned last time, and then having different ideas how you do the order of the work of these chunks. Dynamic is here one that says basically, whenever a thread is finished, it should start directly having the next chunk, while we have learned also static here in this part, where basically the order of the threads were basically the same. And with this, we have seen, without explicitly programming now all the logic of saying, you know, basically different for loops of saying always E0 until a chunk size and the next chunk and the next chunk and the next chunk, and maybe really computing how big the chunk would fit in particularly this overall array size of thousands. I don't do any of this. I just say it should be basically chunked up in 100, and how many threads I have, I don't know, right? That's an important part here. Still, you see the source code is disconnected from the amount of threads that are really put to the problem here, and essentially saying that basically this is scalable again. And of course, we can put more threads here that maybe not basically many threads will execute again in this loop. Or if I have just 2 threads at my disposal, they will interchangeably then working essentially on this for loop. So a very powerful way of doing parallelization, just doing a couple of compiler directives here in front of for statements or marking parallel regions. I have to be careful a little bit with the variables, where I say shared variables, where every thread has directly access to, or where I want to protect perhaps here the private E, similar like the thread ID, which is just for one thread really in the address space, in order to prevent that we basically have problems with loops here, because everybody needs his own indicator where in the loop we want to parallelize. Right, and we will see in assignment 3, when you do your hands-on experience with that this is relatively straightforward. So I think we can go forward here. Of course, take away the message that OpenMP can fill many different lectures. It can actually have a whole training course from Monday to Friday evening if you want. So the centers in Europe, the supercomputing centers, they all offer these kind of seminars where you go much more in detail in all of the power of OpenMP programming. However, today, let us review now what we think about hybrid programming and patterns, which is already connecting to much more, let's say, advanced mechanisms. You learned a lot of basics now until lecture 7, and now we're starting really with having very specific topics addressed, which here and there then comes to, let's say, very particular problems or very particular functionality of HPC. And then from lecture 10 to lecture 15, we will connect with real, let's say, HPC application domains. So the topic of today will be then really reviewing the motivation, why we want to do hybrid programming, what are the benefits in terms of memory, what are the drawbacks of programming complexity if you combine distributed and shared memory programming. You will quickly see that programming these hybrid systems, there are different ways to do it with vector modes or task modes, and essentially saying there are lots of lessons learned that you can increase the performance of hybrid programs significantly, of course, but also meaning that it is a complex topic, so not really for beginners, and it could really, have then really lots of time invested to make really performance of hybrid programmings really work well. So basically saying it is an advanced topic that not every beginner should go for. And if so, you need tooling like performance analysis programs we will connect to in one of the next lectures. Then for the wording, very important today is also that hybrid programming is also something we have to reflect in the world of GPUs and CPUs. So GPUs will be coming in lecture 9, then in more detail, but still people considering today another form of hybrid programming. And just for the terminology, it's important to understand that this is different from shared memory and distributed memory programming. Here we reflect sometimes also hybrid programming as form of using the host CPU computing and the GPU accelerated computing simultaneously for different functions. We will shortly reflect on this, but of course in the GPU lecture we will come back to this a little bit. And then I would give you simulation in science and data science applications context to understand this a little bit. Of course, connecting again to the application we really know already, the HPDB scan, for example. And then in the second part of this lecture, we want to see essentially the situation more broadly. Patterns reflect now basically something where in the next half of the kind of course, really towards the scientific applications, you will see several different patterns I will pick explicitly in order to show you how HPC and certain applications are basically often implemented. It doesn't say that basically all in this particular application domain, they use couplers. They don't basically, basically in the applications I show you, they're not the only ones using partial differential equations or numerical methods. There's a huge field of applications that use stencil-based iterative methods. They actually employ the nearest neighbor communication with Cartesian communicators, you already know. And also, of course, the halo regions, ghost regions, we already alluded to a little bit, is also sort of patterns that you need if you do distributed computing. And at the end, I would stimulate then this with really realistic simulations, again, bringing this coupling of different HPC applications into mind, which is also kind of sort of pattern. So when I also think about now making some forward references in the course here for all the different applications we face in the second phase of this HPC course, they're not arbitrarily picked. They're actually picked for certain purposes where each of these different applications has some unique selling proposition I want to bring to you, like Monte Carlo methods, or essentially, as I said, partial differential equations, law of physics, and so on, and or even this OASIS couplers that really connect different types of scientific applications together. But let us start today with hybrid programming and how that actually helps, and this patterns really helps with having really an understanding of the domain decomposition again. Parallelization, if we do hybrid programming, we will do that at scale. If we do basically patterns, we usually also do this at scale, thinking much more about the domain decomposition. So after this lecture, we really learn how to connect to these problems in a distributed fashion. But of course, we will have the second part of the course, which is all about it, to see how we employ domain decomposition in real science applications. Then, of course, the scheduling will be now again reflected on, especially if you think about that we want to combine shared memory versus distributed memory programming. So I have to put that in my job script that I don't want to have just so and so many threads in one process. Maybe that's the case, but also I want to have different nodes. So the processes on different nodes should communicate, while each of the processes in each of the shared memory nodes should kickstart or spawn different threads. And we will talk about this. And when you do this, you basically have OpenMP and MPI as HPC environment tools already nicely connected to support programming at cutting edge. As I said, it's not a topic for beginners really. Hence, there will be also not a really, let's say, a big practical lecture, but we have a very short part of it in assignment 3. But in the end, it's something more for advanced users here already and not as a beginner course here for HPC. And basically after this lecture, really able to program and use HPC programming paradigms as one of the main outcomes, then leaving out essentially only GPUs, which we have to cover in one of the next lectures. So starting with hybrid programming, from the previous lectures, you already understand a little bit more what it means to have shared memory programming. We learned that on-node communications doesn't really make sense because you remember in MPI, we had always a send buffer and then a receive buffer to transfer data. That means we had to copy the data, so to speak, a little bit as alluded here. When I want to communicate something from one processor to the other processor, I usually do a memory, basically place for it where I can send, and then also having a receive buffer where I want to then have the MPI send receive. So this doesn't really make sense when in a node, right? So there's a memory copy, which is basically not useful if you are in the realm of one node. This one node, of course, means you have one shared memory address space. And it doesn't matter if it's CC NUMA or UMA, you would have basically the protocol ensuring that you have one shared address space. And here, of course, it's particularly quick if you directly read and write from memory on the same node. We learned that already, that the speed of memory is, of course, unbeaten before you go on basically potter off and actually having with this buffering techniques, all these copies created, then message exchanges back and forth. Of course, reading and writing from memory is much more faster. So this is a motivation saying really in order to get the most out of your processes and essentially out of your power that you would have in terms of computing in this core, let's say you want to explore one of these to the most significant degree. However, we learned the problem is we need some sort of hierarchy of that you see a little bit here alluded with a communication network, because essentially this is limit. The memory is limit, the processes that you have here, or the processors with all the cache hierarchies is limited. So what about going the next step? And that means we basically have this hybrid programming now, or parallel computers, which is more parallel computing or parallel programming sort of view, where you basically have a system of a mixture of both, right? You would say distributed memory on the larger scale and shared memory within one node or within the smaller scale here. And this brings us to this idea of the symmetric multiprocessing nodes, which are quite known, but in the end, meaning for us practically, if we want to really program it, we can use the power of this message exchanges across different processes in different nodes and say that we want to do within the node this shared memory programming, because there we have cache hierarchies, we have the shared memory address space where we can really use the threads as much as we can, even if we have the limited amount of memory, because we know in order to then make it bigger, we can transfer some data items and with this message exchanges across the nodes. So this is really an inter-node communication with MPI, and then within the node we use OpenMP. And this is basically a really tuning area. You would say experience suggests really that basically MPI alone is often used. And this has good reasons. It's relatively easy and straightforward. And if you stay with one alone, of course, you basically don't have this problem of thinking about several critical race conditions. You always have the buffers and so on. And of course, you have also not directly this problem of being limited within one node, because in the end, memory is then limited. So the problems you can really deal with are quite small. However, this is something which is, of course, then often used, and is often also used when you combine it with these patterns. Hence, we have the idea of combining both in this lecture today, although we put first an emphasis on this hybrid systems in the first part of this lecture, and then we have this patterns revealed again in the second part of this lectures. So the challenge, however, is when you do this, not only the programming complexity, it also sometimes depends really how you connect the mapping of these different processes and the threads to the hardware architecture this is underneath. It is also meaning that basically the patterns that you really implement, are they supporting, so to speak, this parallel programming concept within the application? Because you come now to very fine tuning, and the fine tuning needs to be supported by the application. One idea could be, for instance, thinking about that a very memory bound application. So you have something which is, let's say, take a lot of memory, and basically the processing is not the problem. So instead of maybe using the shared memory nodes, basically now all for different processing, computing, you rather maybe say you want to have rather the memory shared as an aggregated memory across the whole node, and then one process is working on it, and then just is enough to send message receivers with other nodes. And there are different ways how to think about this. This was just one example. And we will see later in this part of these lectures, especially with the scientific applications following from lecture 11, how this is actually implemented. Obviously, the memory benefits speak for themselves. We have basically the power within the memory within a node. And of course, then by doing hybrid, I have this MPI aggregated power of memory that I can make as my disposal. So definitively going across nodes is important. Still, the question mark remains if you really want to use OpenMP then to do more processing within essentially this node. And in many forms, it makes sense. It's just here and there a little bit complicated to bind them together. And that's why here and now and then it could be good to start first with an MPI implication. And then when you really mastered that, you also have to think about then going basically in the OpenMP space. But there are lots of other aspects which you have to think about, like IO elements, which maybe is also something to think about. Then, of course, also thinking about the overhead of this all different threads and the management of all of that. Maybe it's too much to fine tune, and the gathering of investing a lot of programming time in this will maybe take to an advancement of the advancement of an application which is perhaps good performance, but still the increase in the performance is very, very little. So you have also, of course, a trade, the trade-off between saying you spend hell a lot of debugging and programming for having a hybrid code, but then in the end, it gives you almost no big improvement in terms of basically this, good performance. But it's really an application domain question in the end. Of course, generally scaling up is a very important point, but perhaps MPI in the beginning is good enough for that. And also remember today, we have also this accelerators, right? So accelerators will be a topic where, in lecture 9, we will connect now to this many core systems, how they come in the game. They're not really shown here. Think about that each of these shared memory nodes now has also accelerators perhaps attached. So we also have to think about this in the future. And there the question really remains, what gives you more performance doing then here on the host let's say CPUs, for instance, shared memory programming, or you'd directly use perhaps the accelerator for some certain acceleration. These are questions which are not obvious to you right now. As I said, it's already a complicated or more complicated lecture here today, but then also we need the material of lecture 9 when we talk about GPUs in more detail. However, the general idea to do so is, of course, clear. The memory, the cache hierarchies that we can use and to really communicate between computing is obviously unbeaten. Of course, it's not scaling, but this is what I can do with basically MPI. And you see here that basically a simple example could be here that you have this MPI init thread, and then basically do some pragma statement here, which we already know, which is something doing on chunks, maybe on a very easy setup. And in between, I have my MPI scatter and basically try to really get these variables out to different processes. And then in the end, when this pragma statement was doing its parallelization, then I do the MPI gather again to get the end result before I do the MPI finalize. You see also that the MPI environment is a little bit, let's say, aware of the situation of making it hybrid. So you see here something like MPI thread funneled, which basically says it is basically a requested level of thread support I want to have from my MPI environment. So it is basically used a little bit as a check how it works. And basically you see a little bit here how that could look like on the higher level perspective. So for once, you would say what we learned in the beginning of the course, we always said there's an MPI, there's a process, full-blown process really, but doesn't share any address space, right? So you have these lifelines of these different processes. Now suddenly you combine this MPI plus OpenMP, you basically have still, of course, processors and stuff like this, but there's only one full-blown process leveraging them, while the others are more lightweight threads, still having the advantage then to share all the address space. And of course, being limited to one node here. So in this, you see that a little bit this MPI environment is already thread aware and knows basically different ways how to now, let's say, integrate these threads inside. It's alluding to something we call thread safety. So basically that you guarantee this to the MPI library in its initialization, and you have yourself options to do so, while basically you would say that A here is probably the best understood, or basically D you would see before is basically best understood, because that means MPI only, right? As soon as you start integrating shared memory, the question is on which level you do MPI, right? Do you do it just on the level of the master thread, right? This lifeline we discussed in basically lecture 6 and practical lecture 6.1, or you basically have here, let's say only one in every parallel region is responsible for doing MPI, including the master, but also, of course, some worker threads maybe. Or let's say, is it a wild jungle if you want? So everybody can, anytime, any thread can do MPI calls of sorts. And of course, you can see as an application developer, you have to control this level of parallelism explicitly. So obviously, this one would be probably relatively straightforward to think about, and especially if you think about perhaps Halo regions or so that you want to distribute here with an MPI, maybe some send and receive to neighboring or broadcast or whatever, gather scatters to neighboring cells, and then working with this data in basically the threads and distribute it within the node with threads and working on them. But if you have this wild jungle, you have to really understand what you're doing there. And if it really makes sense to kickstart for every thread another MPI communication, which of course is relatively slow. And the MPI environment tries to basically work again, basically help you there with this thread safety. And when you basically put these configuration options in the MPI init, you have basically a certain level of check if you basically are implementing it to the level of thread safety you wanted. Because big applications in MPI can be quite large, and of course having lots of source code levels, there's many different loops with many different application logics, not only hello world. Think about that in the second part now of the lectures. We will also have integration of really application domain code, so all different levels of physics, and they all communicate together. So that makes a HPC application rather hard and basically rather not easy to read, because there are lots of equations from physics or different, let's say, governing algorithms from machine learning or deep learning that you have to obey. Now, thinking about this fine-tuning, basically that means we starting perhaps with an MPI program, and then suddenly I augment it really with here and there some pragma statements. And basically the best way that how it is understood is probably this one, where you have this, as I said, the master thread doing the MPI. And of course, think about then now with the number of nodes I specify, I'm not done, and also not the number of, let's say, processes. I need the number of threads and per process I spawn. So it's get, let's say, a second level hierarchy if you want. And of course, it is very much useful for very compute intensive use, where you can make use of the shared memory constructs within essentially one node. But then basically we have that not perhaps every processor is really working on this, and others have maybe just pure MPI parts, while the others have more this kind of hybrid / implementation. And in order to think about this implementation, there's kind of two approaches that you would say is vector mode and task mode. And they only basically differ in the degree of interactions and between the MPI environment and the OpenMP environment, which is obviously very important because we want to basically do this kind of multi-threading. We want to go beyond MPI limits and increase the parallelism with this, but we have different ways how to do so, not only by combining this, also when we think about essentially this hybrid vector mode, or basically the other that we will come afterwards. So the work sharing constructs, and here I give you an interesting Fortran code example, so don't worry about this. You basically see that you know, Fortran is very rarely used. Here and there, I come back to Fortran very shortly in CFD applications, because here and there we see some Fortran code still. But in a way, you connect now very quickly, I guess, to the C code, especially if you just consider your basically attention to this statement that you have here. Just to let you also know that the world of HPC is still a little bit Fortran. And with this, I leave it to Fortran, but you see also here this typical do. So it's another word, a for loop that you have already seen, nothing special. So parallelizing the loop in an OpenMP parallel region here. And then I do some essentially MPI application that I already know. And you see already the I receive, I send is very similar, of course, what you have seen already in this C space. And this means I would basically do all the MPI calls outside this OpenMP parallel region, right? Which is a very important factor now for the complexity of the readability and so on of this application. So here I have a very, let's say, good way of disconnecting here now the shared memory from the distributed material computing. You see here, we firstly have something compute intensive within the shared node, then I want to halo exchange maybe, and then come back to the neighbors and so on, and then basically do another iteration of compute intensive based on the new values. So this is something which makes sense to do, and the hybrid task implementation would be basically doing then the other way around, where you would say all of this, as you see here, is indicated as a parallel region, right? And then lead a thread here, you know, for instance, this master thread here, thread ID equals 0, to do something. And then indirectly within this, I would start and kickstart inside this OpenMP parallel region, then my MPI calls to do the halo exchange. And then I have, let's say, another element, which is not the thread ID 0 doing something. Basically is basically good for functional task decompositions, yes, but definitively is a little bit complexer. And I just point to here some code pointers to Fortran, which is still a lively language in a sense. It has its community. And if you are interested, please have a look here. But in the end, you see it's definitively more complex if you do inside, you know, OpenMP than all of these different MPI communication. So in other words, the vector mode is a recommended element, because you don't have really disadvantages. You can do still anytime MPI. You just basically do this a little bit independent from the OpenMP. It's much more simpler, much more understandable to do so. The task mode is really just for experts that know what they're doing. And also here I've seen and heard many times that actually by doing so, you not really gain lots of performance, because here and there, it's really blowing up the source code. It's really increased code significantly, and then you have to do performance analysis tools on top of it to really handle this, because even your brain here and there has limits when you think about lots of different threads. Let's say you have 16 threads or so, and all of them do their arbitrary MPI in between. It could lead to some applications which are really hard to understand, and then obviously to debug. Hence, we know the vector mode would be a little bit the level of choice here, but of course, here and there you have benefits of doing the task mode. That's why people are doing it. And you see the overlapping, for instance, of communication and computation is a benefit of the task mode, making or justify it to really go from the vector mode, perhaps even to the task mode. And there are different other factors, which you would say more or less drawbacks of doing hybrid, basically where the task mode here and there basically has different elements as well, where you have to be careful. But of course, when you manage it, it can lead to basically better performance here and there. Still, for the beginners, and especially here in the course, I would all of you encourage not to start with this. Start with MPI. Once you manage this, go to the vector mode and shared memory, and then think about the task mode, if at all. How that could look when the mapping challenges, I think here and there, of course, you have also different options how you now map these different MPI processes per node, so per shared memory node. You can see that you basically have here always one MPI process, which is here the white one, which is very special, perhaps, and having access to basically all the shared memory power here, and is the one responsible then for doing the MPI, for instance. Or you would do an MPI process per socket, where you're still within the memory space, basically together on this one shared memory node. And then there's a possibility of to do this kind of round robin cross cores in the node, depending on how you basically specify this. Perhaps 2 MPI processes per node that you see here implemented. This depends, of course, now how much memory you really use. It depends on the application intensively, really, how you program this. But essentially also, again, I would say, usually in the beginning, perhaps start with a very simple setup, leverage the whole memory, for instance, for this MPI, and then start to see how much memory is left, how much computing power is here, let's say, usable within this memory space, in order to fine tune then what you can do, perhaps in a compute intensive loop, what you can do perhaps of thinking a little bit about preparing data, or thinking about essentially different halo exchanges here with the MPI processes. And then the real computing should be done within the node and scaling it up then across the different nodes. And this is MPI 1. So also this is usually a bit more elaborate already and not really suggested for beginners. When you do all of this, you see some lessons learned. Of course, especially if you go beyond 3D, beyond 2D, here's the 3D Jacobi application solver that we basically have as one example. You will see also that essentially the kind of Cartesian is what you already learned a little bit from the 2D example I showed you, then 3D. And it's probably obvious that you basically have now 3 dimensions of doing this. And here you have a 3D Cartesian grid indicating it. And the number of nodes you put to the problem, and then basically have this updates per second. The totality details are not, let's say, so important. But it makes sense to see that it is only useful when you have a very perfect scaling pure MPI code. You see, if you do task modes, if you do other nodes, the pure MPI here, InfiniBand and Gigabit Internet, still in a sense outperforms when you have basically InfiniBand networks underneath. So only basically here you see vector mode, and the other ones, they have some, let's say, drawback, of course, and it depends which network connectivity, obviously you have, but if you have InfiniBand, you see that essentially this always gives you a good performance because then the network is supporting this, meaning that the network is a major part in it. And when you do your own, let's say, vector mode on Giganet Ethernet or task mode, so shared memory and so on, you see that the performance tails off very quickly. Hence, basically, we also have to review this statement in the light that we scale higher and higher. We're going towards so-called exascale performance. The question remains if this extreme fine-tuning within one single node still makes sense, yes? And also, if you think about that, the accelerators will grow. The performance and power of accelerators is enormous in the future. Still, also here we see there are basically gains in it. And the HPDB scan we have now often discussed, and you see again here is an example where we do 2 nodes, and each of those have then, let's say, 4 threads. It kickstarts within the node. And with this, you have more aggregated local power for doing the local DB scan algorithm in certain parts of the application. And you see here with the hybrid implementation of, Bremen, or it doesn't matter, even also Bremen, another part of the data set here, you have still the best performance, while the pure MPI implementation at some point in time already tails off here. So basically with the hybrid, we had more linear scaling than doing with a pure MPI implementation. But it's a very specific problem here, because here the local, compute-intensive local part of making this clustering happening in all of these different domain decompositions has some benefit for this particular application. And the Halo exchange in this sense is so-called limited, because it's just connecting some of the clusters I have next door. And we will talk more about, basically then combining this now in hybrid programming with, the so-called many core GPUs. We have introduced this already. So this is largely this accelerators with very many processors here, and will be part of lecture 9. And today people talk about hybrid computing also, of saying, instead of letting the host CPU waiting in order to do just something, like the loading of the data into the GPU, and then no computing power is used at all, and the GPU is doing the processing, we can use the CPU maybe for smaller processing as well, because otherwise it would be idle. Hence, this is a so-called hybrid programming as well, and should be not misunderstood from the idea of actually doing shared memory and distributed memory programming together. So here we talk about a complete different way how to do hybrid programming, and I will talk about this more in lecture 9. It has nothing directly to do with the shared memory and distributed memory you learned in this lecture. Just as a disclaimer, to the end, I would give you here a particle in cell code as a motivating example, or second part of the course, where we really look at some real applications. Again, CFD applications and those that you here see, particulate cell codes, we will review at the second part. And it could be very compute intensive in order to understand, let's say, velocity of particles, stress basically on materials. We will see every different application that we will review basically in our second part of this course. Will have some specific elements. We will talk about why it makes sense to scale up, why it makes sense to get the best performance out of these programs, because there are very many computation intensive parts, or here and there also data intensive parts. Okay, so that's all for the first part of the lecture. So we will talk about the second part of the lecture more in detail with all these different applications, and pick here and there selected patterns I want to bring across within the HPC course. Talk to you then.